Okay, we've been talking about scale factors, and we started off talking about scale factors and linear measurements like length and perimeter. So I want to just sort of pull this all together in a way that will hopefully help you remember which scale factor to use, because in past times of teaching this, that seems to be what students get hung up on. So what I have here is a little 2 blocks, and the perimeter of this shape is approximately that long. Okay? All right. So I'm going to apply a scale factor of 3 to this situation. So it's now going to be 3 times as tall, we'll call it tall, and 3 times as wide. So instead of it being 2, it's going to be 6 wide. Okay, and I'm just pretending these are flat things because this is what I have to work with. Okay. Okay, so it's 3 times bigger in the 2 dimensions, and its perimeter is now this big. I can cut that. Which should be 3 times as long as what we started with. Hey, it is! Look at that! Cool. Okay, what about the area? Is the area 3 times as big? It's not, is it? Because the area is the area of this. This original one is 2, and the area of this, I can split it up. There's a set of 2, and there's a set of 2, and there's a set of 2, and then 3 more sets of 2, and 3 more sets of 2. So the area is 9 times as big. So remember, our scale factor here was 3, and that's the linear scale factor. The area scale factor is 3 squared, which is 9. Okay, and what I want to show you, so it grows faster. That's what I really want to show you, is that the linear measurement, which is a single line, grows at a factor of 3. Which, connect this to the units you'd measure. You would measure a linear thing in centimeters. You would measure an area in centimeters squared. So the area factor, the area scale factor, is squared. Okay, so when we go to volume, when we take our original shape here, which is 1 by 2, and we're going to make that 3 times, we're going to apply a linear scale factor of 3, our volume scale factor is going to be a lot more, because it's going to be 3 bigger in this direction, 3 bigger in this direction or dimension, and it's also going to be 3 bigger going up. So there's my new shape, which is expanded, increased by a scale factor of 3. It's 3 times bigger in a linear way in the length and the width, but it's 9 times bigger in the area, and the volume is going to be 3 times 3 times 3 times bigger, which is 27 times bigger. So I have 54 blocks here. So what I'm trying to impress on you is how much faster things grow. The volume grows much faster. And then conversely, if we're reducing, it shrinks a lot faster too. Okay? And then I want to connect this to, when we talk about volume, we talk about units, centimeters cubed, right? So we're going to cube the scale factor when we're talking about volume. Okay? I hope that helps. Okay, so let's do the math part of this now that we've looked at the manipulatives, we've looked at the blocks. Okay, The original 1 by 1 by 2 rectangular prism was enlarged by a factor of 2. What happened to the volume? So the volume of the actual, the volume of the actual was length times width times height, which is 1 times 1 times 2, which is 2. And the volume of the image, which is the larger one, so we can actually label this. This is actual, this is image. Length times width times height. So now it's 2 times 2 times, or times 4, which is 16. So the volume scale factor is image over actual, which is 16 over 2, which is 8. So the new volume is 8 times as large. And what that is the volume scale factor is the linear scale factor cubed. In this case it's 2 cubed, which is 8. Let's use that to predict the new volume of this cube where it's enlarged, or this collection of cubes, this rectangular prism where it's enlarged by a factor of 4. So the volume scale factor is the linear scale factor cubed, which now is 4 cubed, so that's 64. Okay, because the linear scale factor is the 4 right there. So we have scale equals image over actual, so image equals actual times scale. So the volume of the original was 2, we have that from up above, and our scale factor is 64. That's our volume scale factor. So that equals 128. So the volume of this should be 128. Let's calculate it from the drawing. So volume from drawing. It's length times width times height. So 4 times 4 times 8, which is 128. Yay! Oops, that didn't work out very well, did it? Oops. Gotta do a decent happy face. Okay, so that's how it is. That's how it works. So what we're going to put in our formula box down at the bottom here is that the volume scale factor is the linear scale factor cubed. Okay, and you can make the connection that volume is measured in cubic units, so it makes sense that the scale factor is going to be cubed. Let's do a couple of examples. The Acme Globe Company produces globes with a diameter of 30 centimeters. The owner wants to put a giant globe on the roof with a diameter of 1.8 meters. Calculate the volume scale factor. So both of these numbers that we have been given are linear. It's centimeters and meters. There's no cubed or squared or anything. So these are linear dimensions we've been given. So the linear scale factor is image over actual. And we do have to make sure they're in the same units. So I'm going to convert them both to meters. So that's 1.8 meters over 0.3 meters, which equals 6. So our volume scale factor is the linear scale factor cubed, which is 6 cubed, which is 216. So that's our volume scale factor. The owner knows that the volume of the smaller globe is about 0.014 meters cubed. Use the scale factors to calculate the volume of the giant globe. So the volume of the image is going to be the volume of the actual times the volume scale factor. So the volume of the image is 0.014, and the scale factor is 216. So our answer is going to be 3.024 meters cubed. That was much easier than calculating the volume of something using a formula for whatever the volume of the thing is. Example 2, an oil tank has a capacity of 32 meters cubed. A similar oil tank has dimensions that are larger, by a scale factor of 3. What is the capacity of the larger tank? So the dimensions are larger by a scale factor of 3. Dimensions, that's a linear measurement, right? Length and width. So again, we're given that the linear scale factor is what we're given. That's 3. So the volume scale factor is going to be the linear scale factor cubed. So that's 3 cubed, which is 27. So the volume of the image is the volume of the actual times the scale factor. That would be the volume scale factor if we want to write it that way. So this is 32 was the volume of the original tank times the volume scale factor, which is 27. So that is 864 meters cubed. So it gets a lot bigger really fast. Okay? All right. Go ahead. What I want you to notice here is that you didn't have to calculate, you didn't need the formulas for calculating the volume of any particular shape. In fact, this one we didn't even know what shape the tank is. Could have been, shaped like a marshmallow or a mushroom or a donut. I don't know. Doesn't matter, because if the dimensions change by 3 or 3 times as much, we know that the volume is going to be 3 cubed 27 times bigger. Okay, there you go. That's the end of lesson A. And so go do your practice and then come back and we'll look at the square cube law. All right, let's look at this square cube law. And there's only actually one example that I'm going to do for this part. Let's look at the relationships, just review the relationships between linear scale factor, area scale factor, and volume scale factor. So the linear scale factor is the new length over the original length, or the image over actual. Okay, and that is also used for perimeter because perimeter is a linear measurement. The area scale factor is the new area divided by the original area, image over actual again, and that equals the linear scale factor squared. That's also used for surface area. And the volume scale factor is the linear scale factor cubed, and you can calculate it by taking the new volume and dividing it by the original volume. All right. Most of the questions in this section are actually really similar to the ones that you just finished. There are a couple though that aren't, and you do need to be able to do this kind of question because it takes an extra calculation. An orange has a surface area of approximately 113 centimeters squared, and a grapefruit has a surface area of about approximately 452 centimeters squared. How much more juice would you expect to get out of a grapefruit? So we're making an assumption that the amount of juice that you're going to get is related to the volume of the fruit, not anything else, right? But we're given surface area numbers, so the only information we can get directly from that is the area scale factor, okay? Because that's all we're just given area information. So the area scale factor is the image over the actual. And because we're looking for information on the grapefruit, we're going to call the orange the original. Okay, this is the original, the actual. Okay, it actually doesn't matter which one as long as you're consistent with it, but it'll be easier if we do it this way. So the area scale factor is image over actual. So this is going to be our grapefruit, which is 452, over our orange, which is 113. And that conveniently equals 4 if we reduce that. So the area scale factor is 4. We are asked a question. The question is about the volume. So we need the volume scale factor. How do we get the volume scale factor if we have the area scale factor? Well, you have to go via the linear scale factor, okay? So that's just going to calculate that first. So the linear scale factor is the square root of the area scale factor. My pen is not happy here. So it's the square root of 4, which is 2, and the volume scale factor is the linear scale factor cubed. So that means it's 2 cubed, which is 8. So the orange, or the grapefruit, has 8 times the volume of the orange. So we would expect 8 times as much juice. Okay, hopefully that did not hurt your brain too much. Go ahead and do the practice, and then there's a quiz for you. And that's the end of this unit. Okay, bye.